It is widely assumed that Einstein's general theory of relativity cannot be combined with quantum theory. At least, so far, nobody has found a truly constructive way. In this presentation, it will be shown that the job was in principle already done by no other than the German mathematician David Hilbert, and there is no need to combine quantum theory and general theory of relativity, because the latter already contains the first. A theory of everything, for which we are aiming here, should not only contain Einstein's general theory of relativity, but also all major quantum equations, and it should also explain the appearance of what we describe as matter. In this presentation, we will concentrate on the metric derivation of the Klein-Gordon equation as one of the most important relativistic quantum equations. Our starting point is the so-called Einstein-Hilbert action, a variational integral based on a Hamilton extremal principle. Already in 1915, it was the great German mathematician David Hilbert who derived Einstein's field equations from such a fundamental minimum principle. What Hilbert apparently did not see was that his formula, in fact, contained much more than just the Einstein field equations, but that he had also found the fundament for quantum theory. In this presentation, we will now show what Hilbert had missed, or, taking Hilbert's genius, simply not considered important enough to be mentioned at all. As we have already shown in an earlier presentation that we do neither need the matter term Lm nor a cosmological constant to obtain matter, we set both lambda and Lm equal to 0 and just proceed with the curvature of spacetime, known as the Ricci scalar, as the kernel within our variation. Now, by following Hilbert's classical derivation, we obtain the so-called vacuum Einstein field equations. Things change, however, in a rather interesting manner when introducing a slightly adapted metric tensor with a scaling factor as shown here. Hilbert's variation then yields a much more complex kernel. This kernel can dramatically be simplified by demanding the scaling function to fulfill a special condition. Now we split up the variated contravariant metric tensor into its scaling and its tensor part as shown here. As a result, we obtain two equations, a scalar and a tensor one. In this presentation, we ignore the tensor equation, for example by simply assuming that the variation of the metric tensor gives 0. Then, we intend to fulfill the scalar, which is to say the first equation, by demanding the kernel of the integral to be equal to 0. This gives us a very simple partial differential equation, and by inserting our setting for the scaling function f, we clearly recognize the similarity to the Klein-Gordon equation. The next step is to assume a Minkowski-like spacetime and to split up the Laplace operator in its time derivative and its spatial part. Subsequent comparison with the classical Klein-Gordon equation from the beginning of our presentation then shows us that we indeed have obtained a relativistic quantum equation directly out of the Einstein-Hilbert action by just applying a scaled metric tensor. We realized that in our metric generally relativistic theory, the scaling function, which is nothing else but a volume factor, is just equivalent to the quantum theoretical wave function. We also see how the curvature term takes on the function of the classical mass and potential. It should be pointed out, however, that there are also other options to metrically derive masses and potentials via additional dimensions. The interested reader may find more information in the books shown here or other publications of this author. We explicitly want to point out here, however, that we do not consider us the first to have found the connection. In principle, namely, it all was already inside Hilbert's ingenious approach, and he only could not see it because, at the time he wrote down his equation, the fundamental equations of quantum theory were not yet discovered, and his main goal was the derivation of the Einstein field equations, and thus, as Einstein had not bothered about also finding quantum equations inside his general theory of relativity, Hilbert, as a mathematician, obviously saw no need to consider the broader spectrum residing in his approach. These new insights open up a variety of possibilities for the most astounding developments, be it inexhaustible sources of energy, future weaponry, metric artificial intelligence, quantum gravity computing, or completely new, and what is much more important, truly unbiased and most holistic modeling tools for almost all sorts of problems. And how could such developments be realized? The optimum is the global approach aiming for the quantum gravity computer and naturalized AI, which is a Manhattan-sized project. How this disrupts everything and makes the owner the global monopoly to just everything can be extracted from the material presented in this talk. A next, smaller step is just the naturalized AI, which still is a small Manhattan project. This too already reaches very far and propels the owner into a global monopolistic and long-time leading position, unless somebody achieves a takeover via a working quantum gravity computer tech. Everything else are service projects.